Let's go ahead and get started. So I had a plan, which was I was going to start talking about this domain-specific language called Redex, where the domain is writing down programming language semantics. Okay, and I have a tutorial on this, and I was basically going to work through the tutorial. But then Sam actually presented a really great opportunity for me to just take his lecture and show it to you in Redex. So I'm going to do that instead. So this is available if you'd like to take a look at it, and it'll probably, you could take a look at it after today's lecture, and it'll probably help you out. But I'm going to try to be as faithful to what Sam presented as I can be, and I hope that that's going to help reinforce what was going on this morning, because I thought it was sort of palpable, the feeling of disconnect in the room with what was going on the board, and so I want to make sure that those ideas come across. Okay. All right. So let me talk about Redex first. Okay, so I said Redex is a domain-specific language for writing down programming language semantics. What it really is, or the way that it realizes that, is it's a language for defining sets of, and has a really powerful pattern matching mechanism. Okay, so at its core, that's what it is. It turns out that that's basically what's going on in most programming language papers. What you see is the authors define sets of terms, they define relations and judgments and so on over those terms, and they define these things in terms of fairly complicated patterns, and that's how things are defined. So I'm going to start by showing you just some really simple things so you can get a flavor of what's going on here. So I'm in Racket, and I've required the Redex library, and that is giving me things like this define language construct. Okay, so here I'm defining a set of terms. The set is called L, and actually I should back up. I'm really defining three sets of terms, and those are called M, F, and N, and they live within the language called L. Okay, so it's just a kind of B and F grammar here that you see. You should feel comfortable with this, up to, balancing those parens, which I know is so complicated. We were having having a conversation at lunch about how everyone is really willing to deal with these subtleties of Haskell, but, balancing parens is a little too much to think about. So here I'm saying, I just made this grammar up, okay? It's nothing significant, but I'm saying terms M, they can either be ins, f's, or this next thing is worth talking about, which is here I'm saying that it could be a list with M terms inside of it, and then you'll notice this postfix ellipsis here, which is saying what I'm really saying is 0 or more M's, okay? So if we look at what N means, N is either 2 or 7. So 2 or 7, the numbers 2 and 7, they're M's. The constants Fred and Wilma, those are M's. And if you have some M's and you put them in a list, those are also M's. Okay, so this is just like the inductive definitions for terms that we saw yesterday. Okay. All right, and then let me show you the pattern matcher. Okay, so we can do things like ask if a term matches a pattern. Okay, so that's what this Redex match, that's how I pronounce the question mark. Redex match, of, so I have to give it the name of the language that because the pattern has to be interpreted with respect to some language. So I say I'm asking about language L. I want to know if the term 2 matches the pattern in. And the answer here should be yes. So if I run this, it's true, okay? So I can also ask if it's, let's say, an F. Sorry, I have to use the right keyboard here. If it's an F, and the answer here will be no. Okay, so that's how Racket spells no. And I can also do things like I can write patterns, more sophisticated patterns that aren't just these names. So if I turn this into a list with one element in it, sorry. Okay, that does match. Okay, so let me show you a little bit more about the pattern matching here. This is really just kind of mechanics so that you'll understand the rest of the code that I'm gonna write today. Okay, so so that pattern im ... that matches 0 or more, a list with 0 or more ims in it. Now I could also ask about that pattern, right, and it doesn't like this, so I need to say something like this. So I can put underscores, which we read sort of like subscripts, to mean I'm talking about 2 different occurrences of this variable. So here what I'm saying is, the pattern is asking, does it have a term im in it followed by 0 or more m1s? Okay, and of course it does because the term 2 is an m, so it matches. Had I asked about the empty list of terms, it wouldn't match. Okay, now the other thing that's worth pointing out is I can write patterns like this. Okay, so the pattern here is saying I'm matching a list with 2 m's in it, but because they use the same variable name, what I really mean are there 2 elements that are identical. Okay, so if the term is 1, 2, this won't match. But if the term is 1, 1, it will match. Oh, sorry, yeah. So they're the same, but not m's, right? But 2, 2, they'll match. Okay. All right. So what I've just shown you is really what's sort of at the heart of the Redex language, and then there's kind of things built on top of that. But if you're comfortable thinking about writing these patterns and matching them, that'll go a long way. The other thing I want to talk about is this term constructor. So term, I can say open paren term, and then I can basically write down anything. So numbers, strings, nested things here. All right, and they are terms. If anybody here has ever programmed in a language in the Lisp family, you can think of term just like quote. Okay, so it's saying that the sub form here is just literally the data that I'm writing down. I'm not applying 1 to 2 and Fred and so on. If I write something that you might think looks like a variable, I don't mean the variable y, I mean literally y. Okay, so it's like putting quotes around it, right? Chicago is trisyllabic. If I just say Chicago is trisyllabic, that doesn't type check, right? That's nonsense. The city can't be of 3 syllables. So it's just a way of writing down data. Now, the difference between term and quote is that I can define things, like I can define Sam to be the number 8, and those variables that are defined by defined term are actually interpreted here. So something like that, right? I actually get the substitution of what that variable is defined to be in for the occurrence here. Okay? All right. So let's start with what Sam was doing. All right, and I took photos since we can't see what he wrote on the board, and it's where we ended up at the end of the day, so I'll have to remember about what he started with. But he started by defining a grammar of expressions and values and base values and so on. So I think the best way for me to do this is I'm going to copy and paste some things. Oops. So let me require Redex. And define that. Let me save this just in case something bad happens. Okay, so here I'm defining a language called PCF, and I've got the grammar, and it's just the grammar that Sam wrote down. Okay, modulo some placement of parentheses, like Sam left off the parentheses around application and mu and stuff like that, and I have to write them down just because that's just how you write things down in this language. Okay. Okay, and this is establishing, this is defining these sets of terms, and we can ask if a term is in the set or not, and it gives us these meta variables like e, v, b, in, and tau that I can pattern match against things. Okay. All right. So let's see what the next thing that I'm in the wrong. The next thing Sam did was he defined the type system. Let me find the right slide. So here are the typing rules that he showed. So he's defined up in the corner here, he's saying, I'm defining this judgment that takes a gamma and an expression and it relates it to a type tau. And then he inductively defined it with these inference rules. So I can do exactly that. So let me just bring this over. Oh, I keep doing that. Oops. Okay, so I'm defining a judgment form here. Okay, so I'm defining, so judgments are something that Redex knows about. Every time I define something, I have to define it with respect to some language because that's how the meta variables are interpreted. And then, okay, so the name of this judgment is the turnstile symbol. And you'll notice that, again, because of the way things work in Redex, right, I had to put the turnstile at the beginning whereas on the Blackboard notation, I could put it infix, and that was fine. But here I'm saying, okay, the name of the judgment is turnstile. And then I have to specify the mode of this judgment. So you should think of the judgment as a function, well, really a relation from inputs that's computed from inputs to outputs. And so I have to say, what are the inputs to the judgment and what's computed? What are the outputs? And I can have multiple inputs and I can have multiple outputs. This judgment happens to have two real inputs, which are the type environment gamma and the expression E. And then because Sam wrote the colon, which is just a bit of syntax and notation here, I just pretend that that's an input here, so I can write colon. All right. And then what's computed, the output, is going to be the type. Okay. But then beyond that, things should look pretty close to what was on the board. So here is the typing rule for functions. And the way to read this is just like the way that you read an inference rule. And in fact, I think this kind of will help you develop a crisper model of what's going on in these inference rules. Okay, so when we read below the line, the input positions are given to us. So somebody gave us a type environment and an expression, and I'm saying if the expression matches that pattern that I wrote here, namely it's a lambda term with a variable x, and then I'm using these pattern variables x, tau, and e to bind those parts of the expression I was given. Then above the line, I can use those. So I'm saying that this judgment holds if it's the case that if I extend the environment, the given environment, with x being bound to tau, I can type the body of the expression and get out some type tau prime. Okay, so there it's like I'm making a recursive call with some subcomponents of the input I was given, and I get back a result which matches tau prime. Then the output that I want for the whole thing to be is the type tau to tau prime. Okay, and my environment here, my IDE, is actually helping me show where things, because I don't have some things defined. Okay, so, which is, right, which is maybe the first thing to observe from Sam's talk, right? He doesn't say, like, he just writes down this meta variable x, but doesn't actually say what it is, because we all sort of assume, it's assumed that you know, okay, what variables look like and what they could possibly be called. And also gamma is not defined because we assume you know that. But of course, Redex doesn't know anything about that. So we need to define that. So let's say, what's a variable? So a variable, Redex has this something built in. So you'll notice I'm using, so I can say this. And let me give it a moment for it to catch up here. Oh. I'm surprised it doesn't. Sorry, okay. So variable is something built in, and it's just saying what it means any identifier basically. But that will include a bunch of things that I don't actually want to be variable names in my language. Like I don't want you to be able to name a variable lambda or if or mu, okay? So I can say variable not otherwise mentioned if I can spell it. Ugh. Okay, and what that will mean is if it doesn't occur as a literal in my grammar, then it's a variable name. Okay, so that's a useful little built-in thing in Redex. And Redex knows about number and things like that. Okay, but then what's a type environment? So a type environment is just a list of bindings between variables and types. So 0 or more of these kind of colon pairs. Right? The colon here is not special. It's just, I'm just using, it has the same status as lambda or mu or this arrow. It's just a keyword or a literal in my language here.
Why are we defining gamma in the language? Because it seems to apply to like users and put gammas wherever they want.
So they can't put them wherever they want, right? I can't write if of a gamma and then 1 and 2 and have that be an expression. So it is, I mean, I think the question is getting at something like maybe we want a separate language of expressions and another language of types and type environments and things like that. And in some way we do have that, right? I mean, we have the set of types tau and the set of type environments gamma, and those are distinct from expressions, things like that. I'll show you a bit how we can, in a while, about how you can design languages that are sort of layered on top of languages you've already defined. But, okay. Yeah, so actually the environment was giving me some useful feedback when I hovered over gamma and nothing happened. What it was saying was, what you meant was literally gamma, the character gamma there, which is not what I meant. So I needed to define this. I needed to define gamma, and now it shows up here, and there are arrows. There are arrows from the definition of what gamma could be from the grammar. So that's saying this is what that pattern could potentially match here. And then there's an arrow. I know it's hard to see, but the arrows are directed. There's an arrow from the binder to the occurrence. Okay? So we're pattern matching here based on the pattern that's up in the grammar, and then we're using that the occurrence of the metavariable gamma here, up here. Okay? And we can hover over occurrences and see the pattern and where the binder is, and we can hover over binders and see where the occurrences are, and so on. So we're now binding gamma and x and tau and e and so on, and then if we go above and hover over outputs from the recursive calls, the arrows go in the other direction, right? This is being bound up here and being referred to below the line there, okay? Okay, but of course you've been seeing rules like this again and again, so you should be comfortable with this, but this is really spelling out all of the details of what's going on when you write down an inference rule like this. Okay? So the other thing that you might notice here is I have this, and when I hover over it, I get nothing happens. But I wrote this little thing that I intended to mean the extension of gamma with x and tau, but I actually haven't defined it. So I'm just going to use a little, well, here, let's just define it. Okay, so what that is a metafunction in the language PCF. And here's the definition of the function. So remember that gamma is a list of variable type pairs, basically. And what I want to do to extend the type environment is put the one that you gave me at the front of the list. Okay, so this is like cons for type environments. And I can define it by pattern matching. So here, if you have a type environment that matches this pattern, and you gave me that's how I wrote it. Then what you get back is just put x tau at the beginning. And then all the things that follow that. So a meta function is just a special kind of relation that happens to be not just a relation, but also a function. And here we're just defining it by if it this meta function has one case. Okay, so if it matches this pattern, then we construct this output, and we could add, if we were writing a different meta function, we could have other cases that matched other things. We'll see that. Okay. So now my type environment extension meta function is defined, and if I hover over its use here, I get an arrow from the definition to this occurrence. Okay. Okay. So the lambda case looks pretty good now. The next one is the variable, typing a variable occurrence in my language, okay? And here, this is a place where the type judgment bottoms out, right? It doesn't make a recursive call to the typing judgment, but what it does is it has a side condition about x has type tau if, when you look up x in gamma, you get back a type tau, that type tau. So the where here is a way of writing the side condition. So lookup is going to be another meta function, and it should return the type that x has, if it has one. So let's write that. Ugh. So the first clause here is if I look up, let me write it and then try to explain it to you. So if my type environment matches that pattern and the variable that I'm looking up is x, and notice I'm using the same x here. I've got two occurrences of the meta variable x. So what this is saying is, if I'm looking for x and it's the first thing that's in the type environment, then this pattern matches, and therefore I want tau back as the answer. Now the other case is that it doesn't match. So if I have something else here, then what I want to do is look up in the rest of the type environment. For x. Okay, so this meta function has two cases. They're ordered. The ordering is important here. So the first case matches when you found the variable and you get tau back, and the other one says, well, you only get here if you didn't find it in the first position, so look in the rest of the type environment. Yeah.
That handles the case where the type environment is just x tau?
Yeah, sure. So let's try it out. Okay. So I think this is a good time to start experimenting with things, which is another reason why a tool like, I mean, this is a major reason why a tool like this is valuable. Is you can write a bunch of stuff on the board and think that you've got it right, but you can't, just press run on the blackboard and check it, right? And we saw Sam actually get tangled up in trying to run an example, and computers are great for this. So if I write the term lookup of, let's say x gets bound to the type nat, and that's the only thing in my environment. Okay, so remember how I used define term and I defined Sam to be a number and that got interpreted in my term language? The same is true with meta functions, okay? So you might think that this would just construct lookup blah, 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 but it actually interprets the lookup meta function. So what we get back is the result of the lookup, which is in the type, which is the type nat. Yeah. Okay, so you don't have the turnstile key on your keyboard?
No.
Oh, okay. I guess it's a newer Mac thing, but no, I'm just messing with you. So the way, I should have said this already, but the way that I'm typing these special characters is I know the LaTeX name for the character that I want. So the turnstile in LaTeX is V dash, and if I write slash V dash, and then for me it's control slash, sorry. It's in my muscle memory, but if I just explain it, then I get it wrong. So it's control slash. So like if I want the right arrow symbol, I type that out and then control slash, and it'll turn it into that. And it actually does, you just have to give it a unique prefix. Okay, and it knows about a good set of LaTeX commands, okay, to turn them into symbols. But actually, you could, if you don't like using these fancy characters, right, we can rename these things. Let's call it Bob. Okay. All right, and now the program works, and all of my occurrences of V dash have been turned into Bob. Okay. All right. But yes, I can make examples. I can make examples of my meta function. I can, do things like, let's say I look up something that's not in there. I get an error because the meta function is just not defined in that case. And I can do things like, you want to make sure that you actually get the first one. So if I've got a type environment where x is both nat and bool, right, I'm getting the first one. In fact, there's a testing, I can write unit tests, which I recommend. So I can write things like, here, let me copy and paste. Okay, and I get nothing back there because the test passed, but if I did something that didn't pass, then I would get a notification about the test failure here. So now I can start developing, semantic models the way that I develop software with unit tests and, good software engineering practices, code reuse, things like that. Okay, so now I feel like our variable case is starting to make sense here. Let's see what it looks like to try out a judgment. So judgments are slightly different than meta functions, so I have to use this thing called judgment holds. I called it Bob. So does Bob hold on the empty environment? Let's say the environment in which x is a nat and the term is x. Does that have type nat? I'm asking a question here, right? I'm asking, is the thing that I just wrote down in the Bob relation? That's the question that I'm asking here. And it does. It is, right? Okay. Now, so you can make a conjecture. This under this type environment, this expression has this type, and it will tell you if you were right or not. Now, you can also do something like just ask. You can write in the output positions. You can write patterns. Okay. In fact, in is just a pattern. It matches only in, right? So I could write a different pattern like tau, and the thing that I'm saying here is, does there exist a type? Does there exist a type tau such that these things are in the relation? And the answer is, of course, true. And in fact, if I want to know what that type is, I can I can give judgment holds two things. I can give it the use of the judgment, and then I can refer to the pattern variables that I was binding over here and get them and have them be returned to me. So here I'm saying, is there a type? And if there is a type, let me know what it is. And now you'll notice that it's giving you back a list of things because it's a relation. There could be many types in general, right? Not in this particular case, but in general, there could be many types that expression could have, and it will give you back all of them. Okay. Right, and if we write something ill-typed, like apply 1 to 2, we get back the empty list because there are no types right? There is no type tau such that this is in the relation. Okay? Good so far? All right. Let's look at the rest of this. So I think the rest of it is going to be pretty straightforward if you're comfortable with those two cases that we've done. So here's the application rule. All right, we're making two recursive calls. Notice that there's this. We have two uses of the meta variable tau, so those types have to be identical to be for something to be in the relation by this rule. A literal number has the type nat. So notice there's no. If we wanted to make it look more like the other rules, I should have done this. Right? We can write this overline. Right? With nothing above it. There's no preconditions. A number always has the type nat, and the same is true here with the Booleans. So. And it doesn't matter how many think you have to write at least 2 or something, but it doesn't matter how many of these you do. Okay, so these are just the typing axioms. Here's the if case. Okay, again, notice that we've got this double use of tau here, so those types have to be identical. Okay, and then Sam didn't show some stuff because he said it was boring, but of course, if we're going to run things, we need to define it. So Sam's examples use things like asking if something is 0 or odd, so I need typing rules for those, and plus. Okay, and in fact, I need to have definitions of what is 0 is and things. So let me just pull these. Oh no, I think so here. Right, Sam never actually nailed down what ops are. So let's do that, right? So the operations I have are plus, is 0, is odd. Okay. All right, and now these typing rules are all. Yeah, well. Yeah, yeah, sure. Yeah. We've had enough of Bob. Yeah. All right. Okay, so that was the typing judgment. No, let me show you some other things that we can do. Just some other nice features of Redex that we can see so far. So one thing is, it's sort of one thing to do these examples like this. Let's do something a little more involved. So maybe we'll write a function that takes in a natural number, and it produces a function that takes in a Boolean, and then it does, if the Boolean will do 6 plus x, otherwise we'll do x plus x, right? And oops, I got my supplied 3. Oh, I didn't give it a type environment. Okay, so that expression has type nat arrow bool arrow nat. But maybe I want to actually see the proof that this expression has this type, so I can do that with this function called build derivations. Okay, so I'm going to show you this. It's going to return this list of derivation things. That's really just a data structure describing the proof tree here, but there's a nice little helper called show derivations that consumes that data structure and will pop up a window. So I don't know how many of you have taken, graduate PL courses where they've asked you to write, a derivation, and now you can just, do this and print it out and give it to your professor. Okay, and we can make the font a little smaller, and we can tweak how it prints everything, but right, it's showing it to us, which is nice. Okay, so if you want to design a new type system, and I suggest that you put examples in your papers, this can help you figure those out and double check that you get them right. Okay. All right. So the next thing that Sam was showing was the dynamic semantics. Okay, so he did the static semantics, and then he showed the dynamic semantics. And one thing I saw go by on Slack was that this is sort of part of the disconnect that happened was I think Bob and Frank and Dan were all presenting dynamic semantics in a different style than what Sam was doing, and that could be confusing. Not that he's presenting anything different, it's just a different style. So I thought I'll show it to you in the way that Sam did it, and then I can show it to you using the kinds of rules that the other speakers would have used. Okay, so let me just make a note about that, and then let's go back to copying and pasting. Oh, sorry, wrong thing. Okay, so the first thing Sam did was he defined this notion of an evaluation context. So let me add that to my grammar. So this is literally just a transliteration of what Sam wrote on the board. And the only thing unusual here is that first possibility for what an evaluation E could be, which is this thing called whole. That's a built-in Redex thing. Okay, so Redex knows about wholes, and that's going to be useful because we'll be able to define things in terms of evaluation context and do things like decompose into contexts and inner expressions and recompose and things like that. Okay. Right, the way Sam wrote it was with square brackets like that, but this whole thing is built in to Redex, so I'm going to use that here. Okay, and then Sam defined the reduction axioms. So let me pull those over. Okay, so this is another Redex thing. I'm going to define a new kind of relation, a special kind of relation, which is a reduction relation. Again, always in reference to some language, so this is going to be for the PCF language. And then the way that a reduction relation is defined is by a number of cases. The order here does not matter. Okay, I can reorder these in any way, and it doesn't change the meaning of this relation. But each case has a pattern and a constructed term on the right-hand side, and optionally, it has a name for the particular case in this reduction relation. So this case is called beta, and its definition is if you match that pattern of being an application with a lambda term and a value, then that reduces to the substitution of v for x and e. Okay. Now, subst is currently not defined, and I'm not going to bother spelling it out. I'm just going to import my definition that I already have for it. Okay. And now subst is defined, and it should do the right thing. Okay. All right. Here is mu. What Sam called mu. What I think Bob and others called rec. Okay. But same thing, different notation. Is substitute the whole thing itself in for x in the body. Here are the rules for if. So if true, then you get E1. If false, you get E2. And then here, this is something that Sam spent a little bit of time on because it was totally confusing on the board, but it's completely clear here in the code about font changes and things like that, right? On the left, we're talking about, we've written a pattern, just like in all the other ones, where we're saying something that matches in one, and then literally the plus sign, and in two. And then you'll notice here I've got this this comma character, which is pronounced unquote. And what I'm saying is I'm not in the term language anymore. I'm escaping out of it. And I'm now in the meta language of Redex, which is racket. Okay? And I'm saying I want to apply a function which is the plus function, the thing that takes numbers and adds them together. I'm applying that function. It is not, notice there's no arrow here. I'm not even in Redex world anymore. I'm just writing down a racket expression. So I'm saying I want to add two numbers together. Which numbers? Well, go back into term world and get me the number that's bound to n1. And that'll be the first argument. And then the number bound to n2, that'll be the second argument. I add those two numbers together. And that's the term that I'm producing here. So that's how plus works. And the tool will tell me, notice it's saying that plus imported from racket, right? That's racket's addition function. Okay. And then I also implemented the operations that just weren't shown on the board, but is 0 of a number? I again escape into racket world. I use racket's conditional form if to ask if the number is 0, and then if it is, I want to produce the term true, otherwise the term false. Okay? Okay, and at this point, right, we can do things like apply. Okay, so let me run it and then show you some examples. So I can use this thing called apply reduction relation. And what it takes is the name of a reduction relation, like R, and a term. So let's do the term 1 plus 2. And what we get back is a list, because we get back a list of things that term reduces to in one step. Okay, so right, so if we did if true 7 and 2, in one step we get 7, so on. But if we do something, so one thing to notice, what's not in this relation is something like 1 plus this stuff. That doesn't reduce to anything. So why doesn't it reduce to anything? All I heard was which is exactly right. It doesn't reduce to anything because we need to reduce in the context of the 1 plus here, but the R relation doesn't include that stuff, so it's just stuck, right? So we need another relation. So I'm going to call it arrow R, and this I'll show you how we can do this. So I always forget what the order of arguments is here. I think it's R PCF E. So let me just try this and. Okay. So arrow R is another reduction relation, and it's defined by taking the contextual closure of R over the grammar of evaluation context E. So up above, I had that definition here, E. And remember that, I said Redex knows about that whole thing, and what this context closure is doing is just that rule that says, if E is related to R by the R relation, and there exists an evaluation context that E is inside of, then this thing is in the arrow R. Okay. Okay, so that's just what that thing is doing. Yes?
When you apply reduction relation, it's also taken for the syntax internally. You're given it a term.
Yes.
It's also taken for the syntax before applying the reduction relation.
Yeah, that's a good question. It is not. Okay, so I can write things that aren't actually PCF terms, right? Like we didn't add strings to the language. So that thing that I wrote there is not a term in the language PCF. And what I get back is that it doesn't reduce because that isn't in the relation, okay? Which is correct, but might be frustrating, right? Because it's not like you didn't get an error. It doesn't say, what are you even thinking trying to reduce something that's not a term in the language, which would be useful feedback. It just says it doesn't reduce to anything. So we can do a little better and say that the domain of our reduction relation is E. Right? This is a binary relation on expressions, and so we can declare that, and then it will be checked. Okay? And so the domain that I write down here is, again, just a pattern. Okay? I could write down anything, but what I want to say here is it's defined on any expression, so the right pattern to write is E. And now I will get an error, okay? It's not statically checked, okay, but it is checking this as I run it, okay? It turns out the way that this is implemented under the hood is with contracts, okay? All right. I can do the same for all of my other judgments as well. So I can declare a contract on the typing judgment. Okay. Which is just the thing that Sam wrote down and put a square around when he wrote the definition, saying that this is a judgment that takes a type environment, an expression, a colon, and a tau, and gives you back a tau, I should say. And now that will be checked as well. So if I ask something like, does the judgment hold that in the empty type environment is the string Fred, does it have a type? Okay, before I would have gotten back the answer no, but a more sensible thing is to complain and say that's not even a well-formed question because it's not. Sorry, I left off the S here, and then I get a totally not helpful error message. But I get an error saying that this was the contract for that judgment, and this doesn't match that. Okay? And again, the contract is expressed as a pattern. So if you give it inputs that don't match, these patterns, or it produced an output that didn't match this pattern, we get a contract violation, and it blames the right person, either the user of the judgment or the judgment definition itself. Okay. So again, very useful, worth emphasizing that it's not static. I can write down a definition here that's junk with respect to this contract, and it'll only fail once I actually run the judgment. Okay. All right. So let's see. Let's now run a program. Okay. We did the apply reduction relation, but remember that just does once. So that was my bad example. It just does one step of reduction. Okay, there is a variant of apply reduction relation. Oops. Sorry. That will iterate it. So this is going to, what this gives us back is the list of things that you can get to that are irreducible. Okay? So it gives you back the sort of final answers here. Yeah?
What if the operational semantics is not deterministic?
That's why you get a list. So you get them all back. So why don't we add that? Let's just do this. So let's say either. We'll add a new construct to the language. I won't give a typing rule for it because let's just see how it runs. So we have a bunch of different choices for how to do this, but let's do it this way. So if you have the either of v1 and v2, well, you get either of them. And I now need to go back to my evaluation context and because I need to be able to reduce inside of an either, so I'll do it like this. I'll just make a choice to do the left one first. We can go back and make different choices in a second. Okay, and let's do this. 1 plus either 7 or 2, and you go back 3 or 8. Okay? We can visualize this by, instead of calling apply reduction relation, using this tool called traces. And you'll get a graph mapping out all of the steps of the reduction relation, and it will label. We didn't give names to the either rules, that's why there's no labels on these arrows, but notice it's labeling the plus reductions here. Yeah? Yeah, that's a good question. So we can certainly make examples of that, right? So that should diverge, right? Okay. So yeah, that is nice, right? It's telling you this is a program that takes an infinite number of steps, and it does it by stepping to itself. Now, you might wonder, well, what if what if you can't just finitely summarize what's going on here, like if we did 1 plus x? Okay, and the answer is you get to see some of the reduction graph. So you'll notice here it's saying I've got, down at the bottom it says I found 21 terms. There's possibly more to find. And it shows each of the steps of getting those 21 terms. And if we want to see more, then we can keep reducing it. Okay, so now we see 41 and... why did it stop at 21? It's just, it goes for a while and then it stops. I don't really know why it stopped at 21. And so we can see some of these terms are now are getting bigger. Sorry, Will, what was your question?
If you went back and didn't do the graphical thing, you just went, show me the list of...
Yeah, okay, so, yeah, let's see. Close that. So if we go back to apply reduction relation, star, in the first example, we get back the empty list because there are no irreducible terms that you ever get to. And Redex figures that out. Okay, so it answers, right? It says there are no irreducible terms that you ever get to. It cannot figure that out in this case, okay, and it will just run forever. And I think there are if you want to read the documentation about apply reduction relation star, I think maybe you can set timeouts and limits and things like that, but it would just run forever. Yes?
What if you like apply reduction to either one? Will you get a list of left to a left one?
You will just get if I apply it to either, like that?
1, 1.
1, 1. Yeah, that's a good question. So it's giving me back a list representing the set of terms that I get to. The same is true when I visualize this. Right? This either 1, 1. There's only one term it steps to. Okay? So it has some notion of equivalence between terms, and the default one is just syntactic equality. But in fact, you can define your own equivalence relation. And then, so one thing you could do is define alpha equivalence, and then if things step to two terms that had different representations but were alpha equivalent, they'd be collapsed into one in the graph here. Yeah. Sure. Yeah. I mean, if you can define it as a reduction relation, you can do it here. Okay, so so one thing is that this is maybe let's do this another way, and we'll see a little more like kind of intermediate non-determinism. So instead of that reduction relation, why don't we, like, let's imagine I did, instead of that, I did something like that. Okay, and now you'll see, right, there's many different ways that this could reduce, because we can either choose which subexpression we want, or we can reduce within them. Okay, so, and all of that is fine here, and we always end up with either 3 or 4. All right. Okay, the same is also true, right? So what Sam showed was a standard reduction relation for PCF. He picked a strategy for how things would reduce. We could talk about just general reduction, so let me call it arrow R prime. And then I'm going to use a different sort of reduction relation combinator here. So here what I'm saying, so compatible closure, you give it a relation and a pattern for terms, and it will let you reduce inside of any sub-expressions. Okay? Whereas this lets you reduce inside of any context. This lets you reduce inside of any sub-expression. And now I'm going to take I won't use either, but we'll, if we look at something like 1 plus 2 plus 3 plus 4, I better do prime here. We'll see that there's different ways to reduce this, and the same is true with, if we wrote lambda terms. So if we wrote x is a nat, produce 1 plus x, and apply that to let's just do the identity function applied to 5. Right. So this example didn't show what I was expecting, but that's because what I have right now is the call by value lambda calculus. So even though there's different places that you can reduce, the argument here is not a value yet, so it has to be done first. We can relax that by changing our beta here. So let's call this E1 and substitute E1 here. And now you'll notice that we can do those applications in different orders, right? Okay. All right. Okay, so what else did Sam do? Well, so I want to show you that you could write things in the structured operational semantics style, where you write the dynamic semantics as a judgment, okay, which is more like the style of what Bob and Frank and Dan did. I started to fill this out here. So I wrote the case for beta and mu, and then we can have the inductive cases like if. Okay, let's do plus, because that's easy. Okay, so if you have step of E1 plus E2, that will step to E1 prime plus E2 if E1 steps to E1 prime. Okay, and then if you have that E2 steps to E2 prime, right? And then we have some more cases to fill out, but that looks a lot more like the form of dynamic semantics you saw earlier in the week. Okay. Now, this isn't a reduction relation, so I can't use my traces tool with it, and I can't say apply reduction relation, but I can build derivations that show one expression steps to another, just like I could build derivations about things being well typed. Okay? And in fact, if I wanted to use my traces tool, I could define a reduction relation that just sort of deferred to this judgment here and say that the expression steps to another if the judgment holds that that expression steps to that thing. Okay, so you can formulate the semantics however you feel comfortable here, and then with a little bit of wrapping around it, you can still use the tools to run examples with it. Okay, so we're running, getting close to running out of time. I wanted to do, I was going to do the example that that Sam had, but that means I have to show you the contract language. So why don't I just show it to you real quick, okay? Because now you should feel fairly comfortable with how Redex works. So here, this is what I said I would show you how you can build a language on top of another one. So here is the CPCF for contract Pacman computable functions. And it's defined as an extension of just Pacman computable functions. And that's what Plotkin meant by PCF. And you'll notice I'm using this 4 dot ellipses here. And this is the kind of like, you see this stuff in papers all the time. They start with some language and then they modify it later by saying, well, it's just like that, but we change it up in this way. We might add a few features. So here I'm adding some features. And what I'm saying is that the meta variable E, if it's interpreted in the CPCF language, then it means all of the things that I had in PCF plus these things, okay? And that kind of sounds obvious, but it's subtle because it also means, like, if you go back and look at the PCF things for E, that these occurrences of E here are reinterpreted in terms of CPCF here, okay? So it's as if I had just taken all of this stuff and copied and pasted it into the 4 dot ellipses here. Okay, so I extend the expressions, I extend the types, I extend the evaluation context. Here is what contracts are. They're either flat of some expression, function contracts, dependent function contracts. Okay, and I made some slight changes, like, so I got tired of seeing all of those labels. I just made them a single 3-part thing here. Sam never said what a label was, so I'm assuming it could just be anything. Sam also used the meta variable k to range over both labels and contracts. I don't know if anyone caught that, but that was super confusing. And I made a list of mistakes that Sam made because, well, I wouldn't have caught them if I hadn't done this, if I hadn't modeled this stuff while he was up here talking about it. So this is really what Redex is great for, is if you're reading a paper and you want to understand what's going on in it, fire up Redex and write down what the authors wrote. Try out some examples. They will have made mistakes, okay? Even in published papers, there will be things like, oh, K got overloaded to mean two different things, and it could be confusing. But you will really understand what's going on if you do this, and you can try some things out. So he overloaded K to mean two different things. He overloaded the type judgment relation. Did anyone catch that? It's supposed to be a judgment. He wrote down. There are tapes. He wrote this down, that the type judgment relation is about a type environment and an expression, lie, right? He's lying. Totally unfair. Because let's look at his fake judgment. Where is it? Right here, notice that he is inductively referring to a judgment on contracts, and contracts are not expressions. Okay, so I caught that, and I pointed out while he was talking that he left off some type annotations in one place, but he actually left them off in another place that is a little more difficult to deal with. Let me see if I can enhance. Okay, so look at this reduction rule, the one that Sam said was the crucial one, and it is. All these mistakes are small. There's nothing fundamentally wrong here. I'm just making fun of Sam, but here's a little mistake, right? When you're monitoring a function contract against a value, you delay the checking of that contract by doing a form of ADA expansion here. So it turns into a function that will monitor the monitor the output of applying the function with K2 after you apply V to the monitored input with K1. But remember that in this language that he showed, lambda-bound variables have type annotations, but this one doesn't. So the first time I caught Sam with this, it was easy to fix it. But what do you do here? What type should you write down? Yeah. I do know Sam gets to talk again. So Sam and I used to co-teach classes, so this is actually, we're quite comfortable with this dynamic. Yeah, so he's missing this annotation here. So here's how I fixed it, which is, you know that, so you know that V is a function, right? You're applying it right here. So instead of just saying V, let's pattern match on a lambda term, and then we have the type, and that's going to be, it's the same type, the function that you expand to, should have the same type as the one that you're monitoring here. Okay, and then Sam wrote this this example, and this is what he wrote. This is what he wrote on the board, and this was the example, and it should have ended up blaming K. Notice K occurs twice in that example, so so when I wrote it, I did it a little differently. So here's what V is. It's just exactly what he wrote, but also writing down the type annotations that you need. Here's the definition of that context. Okay, so it's got a hole in it. Here's the definition of the contract K. So I had to define what so OHA is odd, and any is just the flat contract that produces true. And then the example, e.g., is just that context we defined with this monitor expression in the hole. Okay, so if we if we look at this is the example spelled out, okay, and if we want to run it, well, we could maybe first check that it's well typed, and it is. If you want to know what the type of it is, it's NAT. And we could build the typing derivation, or we could just run the thing. So here, this is the code that I wrote while Sam was typing. So I didn't actually R prime is the PCF reduction relation lifted to CPCF. Okay. So usually in papers, that's just implicit, but here I had to be explicit about that. So let me show it to you. Where did that happen? Here. So R prime is just R, but I want those patterns that I wrote to be interpreted in CPCF, not PCF. Otherwise, they'll be stuck expressions that I wanted to reduce. So, so R prime is like the PCF reduction. C prime is the fixed up CPCF reductions dealing with contract checking. I take those two relations, I union them together, and then I do the contextual closure over evaluation context E. And then I can try it on my example. And what we'll see is, so I can, let me mention a little bit about how I said that I sort of cleaned up the labels. I did it so that the labels, there's three parts to them. It's about the context, value, and the person who wrote the contract. And then in that crucial rule where things swap, I just have a meta function called swap that switches the parties, okay? And then in the case of check and error, it's the first part that's to blame, okay? And it's the third part that is the party that wrote the contract, okay? So that's how we can interpret the, so here it says there's 21 terms with possibly more to find, so let's keep going. It eventually bottoms out after taking 21 steps to this thing, which is not a value. It's actually just stuck, and it's stuck because it has this error term inside of it. And like I said, that it's when you have an error, you're to blame the first party listed here, which is Q, which is what Sam conjectured. That's the party that should be blamed, and we can confirm it without getting tangled up or doing the reductions in the wrong order or anything like that. Okay? and we can see all of the work that goes into that. So it was a little ambitious to think that Sam could have worked this example out on the board anyway, right? Because, but he was right. It does blame Q. Okay. All right. Are there questions on this? Yeah. So there's no checking going on. I can and this like I was saying here that the domain here is E. That's not checked. That's not checked statically. So I can write things that are nonsensical like this, that the string Fred reduces to the string Wilma, and oh, it actually does. It does check this. Oh no, that's just because yeah, there we go. I was going to say, it's been a while since I've used Redex and it's gotten fancier, but no, it hasn't. It's perfectly fine with this, okay? It will, so this reduction, if you were to apply it to the string Fred, it would raise an error saying that Fred's not in the domain, okay? Even though there's a rule that applies to Fred. And if we were to change it to something, like this, where you gave it whatever E and it reduced to Wilma, you would get an error saying that the reduction relation is buggy because it produced something that's not an expression. But if you don't write enough test cases, then you won't find that out. Okay? So there's nothing fancy going on statically. And that's in part by design. You can write down whatever junk you want and then see what happens when you run it. That's why it's a useful tool for using as you read papers, because people make mistakes and you can still write it down and then find out what happens with it. Or as you're developing something, you can just try out ideas. You don't have to have them all totally correct in order to start running your program. So this is really, so there's a good talk by Robbie Findler, who's the main developer of Redex. A keynote, no, sorry, not a keynote talk. It's a Popple talk called Run Your Research. And that paper is about case studies where the authors took a random or semi-random selection of papers from an ICFP proceedings and modeled them all in Redex, and then discussed all of the errors that they found in all of the papers, okay, including the Coq-verified ones and things like that. Now, some of those errors are things like, meta variables get overloaded and, small things that happen. And there's a video of that talk. I highly recommend it, okay? And the way that Robbie thinks about this language is it's like a scripting language for programming language semantics. So you can get off the ground running, try things out, explore, experiment. In my own research, this has been just an incredibly powerful tool to help me think through things and experiment with ideas that I have. So I really recommend it. Robbie also argues the case that you should, model your semantics and type systems and things like that in Redex, and then go directly into the paper so that you don't introduce typos when you convert from this into LaTeX. So let me just show you how you can do that. So it's the last little bit. So all of the examples of the derivations, you can render those to PDF and then just include them in your paper if you want examples. You could also use the Racket language for typesetting things and then just call it directly and have it be generated. But there's but there are ways of typesetting meta functions directly. So let's see this. Okay, so let's look at like render language. Oops. Let's do CPCF. So just the language. Oops. Oh, I'm in the wrong file. Okay, so notice it produces an image. You'll also notice that Dr. Racket is totally cool with things like this in your source files, but it renders an image that you could include in a paper that's like, this is what the grammar of your language is, and you can do this with things like meta functions too. So let's do it with the judgment. So render judgment form. So the turnstile C judgment form was the typing rules that had to do with contracts, and we get this nice looking set of inference rules that we could include in a paper. And now some of the notation is maybe not what maybe you want to use something different than this kind of S expression based syntax, and you can write custom printers for your terms and things like that and actually make it look quite nice. So if you want to see good examples of this, Asumu Takakawa has nice papers with that are all Redex generated figures and things like that. Okay, so you can write it in Redex, you can make examples, you can write unit tests, you can actually do property-based random testing of your semantics, and then you can just generate the figures for your paper right off of the actual code that you've tested. Okay, so it's quite nice. Maybe the last thing I wanted to say was, how I said that typing judgment was that Sam wrote. Right, I made this note about these are not expressions, right? Flat E is not an expression, and K1 arrow K2 is not an expression. That's something that I could have caught. So this code is totally cool, right? Redex is we'll just take whatever you wrote down, like you did on the blackboard, and run it, and that's fine. But if we had actually declared the contract that Sam wrote, here, we would get errors. Okay. right? So it would catch things like that because there are places where that thing is not a contract. All right, any other questions? Yeah.
So I understand racket LP is defined by some hash lengths.
Mm-hmm.
Can you export this or something like that?
Yeah, so that's a good question. Right, you've probably noticed that both Sam and I we write these programs that start with hashlang racket, which is declaring that the programming language we're using is racket, which is weird since this is the racket environment. But it turns out that racket is itself a language for writing languages. And so there are other kinds of languages that you can write. Sam showed you typed racket, which is sort of a typed variant of racket, and you can make other ones too. The answer to your question is yes, you can make your own hashlang language that's based on a Redex model, but it takes some work. It's not something as simple to do as the other stuff that I've shown here. But that's nice because then you can just write down programs directly and hit run, and it will use your reduction relation to figure out what the result is and print it out, and you can have a little REPL where it's actually your language that you built rather than Racket running Redex running your language. Yeah.
I was interested in how hard was this to implement, like the Redex, the whole thing?
I don't know because I didn't implement it. All right, I'm just a user of this system. I think the answer is, it's been in development for many years, actively developed. There's papers published about Redex. So there's papers published about Redex and how it's implemented, and then there's papers published about using Redex to model existing papers and things like that, and you can read about that. And the person to ask is Robbie Findler, but it's taken a fair amount of effort. If you think about the pattern matcher, right? It's sophisticated. It's not so straightforward to implement that. Yeah.
If I just pick up a random paper, how many lines of code do I expect I need to write to actually write down the semantics and types and whatever?
I don't know of a good answer to that question in general, but I can give you an example, right? Sam wrote some stuff on the board that is like what you would find in a POPL paper. In fact, I think this is what you would find in a Toplis paper about contracts, dependent contracts. And I'm basically in one-to-one correspondence with the lines that he wrote, okay? So I could, back up over some white space here to make it look more like what he wrote, but my grammar definition looks just like his. My evaluation context looks just like his. My judgments, I've got one judgment for each judgment he wrote, or one inference rule for each one he wrote. I had to define some meta functions, okay? So like lookup, extension, and substitution, okay? Do you want to see the awfulness of these? Okay. Extension, we wrote that actually together. Lookup, that's easy. Substitution, it fits on a screen. Right? It's not that bad, but that's substitution. So, I think you should not expect to write many more lines than what you would read in a POPL paper. It sort of depends on how the paper is written. Sometimes things are omitted, and you can't just omit them from the code. On the other hand, you can build up reusable pieces and reuse them among many papers. You can be the judge, but I think it's pretty close to what you write down on the board or paper or whatever. Any other questions? Yeah.
I think this morning I was
So I missed that. I missed that rule. Yeah. Okay. Good. So let's fix it to do that. Yeah, we're way over time. Maybe I'll do that and show that at the beginning of my next lecture. So Zaina told me we're on Italian time, and I'm. This is my interpretation of Italian time. Okay, well I'll show that next time. But yeah, you can express rules like that for sure. All right, I should stop there. Thank you.